Why does the universe exist? Scientists say it was the Big Bang, which sounds simple enough, but leaves a lot unanswered. What exactly does a Big Bang entail? Before we get into the origins of the universe, we need to discuss what the universe even is. The universe is made of matter and energy, so before we go any further, we should know a little about either of them. Minor disclaimer. Aside from a lot of this being theoretical, much of this information will be very simplified to fit in the time span of the video. Let's talk particles. You can't have a universe without stuff, and the most basic of this stuff is a particle. The particles we discuss will by no means be comprehensive or complete, but a general overview to give some perspective during the meat and potatoes of the Big Bang. First, there's hadrons. Hadrons are composite subatomic particles, a combination of two or more quarks held together. But you don't need to know all that. Just know they are the bigger of the subatomic particles and are mainly protons and neutrons, which make up the nucleus of atoms. Next up, we got the little ankle biters, leptons. These guys possess only one quark and are significantly smaller than hadrons. These are your electrons and neutrinos. You usually find them speeding around and in between atoms. But that's not all. There's actually an evil version of each of these particles. Instead of being matter, these guys are called antimatter. And when they touch matter, they just blow up. Something to do with them being the opposite charge, I guess? I don't know, man. I just work here. Next is the energy of the universe. Energy is transferred in a couple different ways, called the four fundamental forces: gravity, electromagnetism, strong nuclear force, and weak nuclear force. Each of these forces have their own little quirks and gimmicks, so we'll go over each of them. Let's start with gravity, one of the easier to understand. Unlike the other forces, gravity can only attract. Gravity scales with mass and distance, and you can't get negative mass or distance, so it's only ever positive, only being relevant at macroscopic scales like galaxies, planets, and the likes. Next, there's the electromagnetic force. It's relevant at human scales to the scale of electrons. As well as being stronger than gravity, the electromagnetic force is based on the charge of particles, so it can be both attractive and repulsive. This force is not only responsible for electricity and magnetism, but also light, friction, and even dictates chemical reactions. After that, we get to the atomic level. First, the strong nuclear force, which confines quarks to their hadrons. In other words, this guy keeps protons and neutrons as protons and neutrons. It gets its name from being the strongest of the four forces. The final force is the weak nuclear force, which gives us radioactive decay. Responsible for nuclear fission and fusion, this force is objectively the weakest and only has a significant impact at smaller scales. But even a weak force like this can cause quite a ruckus. Now that we know what's up, down, strange, and charm, a little reference for the quark lovers in the audience, we can finally go over the Big Bang. We don't exactly know what the beginning of the universe looks like, but we do know what it looks like 10 to the negative 43 seconds after it starts. Like this. Right now, the whole universe is in a space smaller than an atom. All four fundamental forces somehow are the same force, and the energy causes this point to be 10 to the 32 degrees Celsius. This is what the science guys like to call the Planck epoch. Shortly after the Planck epoch, after about 10 to the negative 32 seconds, gravity separates from the rest of the forces, and the universe begins to expand. This is the grand unification epoch. The universe is still incomprehensibly dense, but it's making some moves. The next force to separate is the strong nuclear force during the inflationary epoch. At this point, the universe is about 10 centimeters in diameter and expanding rapidly. All the mass begins to distribute across it in a quark soup. This is because scientists don't like salads. After that, we're in the electroweak epoch. Until around 10 to the negative 12th seconds, all the quarks mix and match in the universe to create many exotic particles. From then until a millionth of a second, we see quarks, electrons, neutrinos, and whatnot form in much greater numbers. This is creatively named the quark epoch, Electromagnetism and the weak nuclear force finally separate. Took them long enough. Anyways, the universe is now cooled to 100 quadrillion degrees. Matter and antimatter collide in baryogenesis. They just do that. Particles of matter and antimatter just appear and collide into each other, canceling each other out and disappearing. But at this stage, for some reason, slightly more matter appeared than antimatter. 1 out of a billion regular matter quarks survive, creating a surplus of regular matter. Hadrons, like protons and neutrons, finally begin to form from a millionth of a second to 1 second. It's still about 1 trillion degrees, but we've actually been able to recreate that temperature in the lab. Right now, the universe is in the hadron epoch because of all the hadrons. Don't get too attached to those hadrons, though. They're still colliding with their antimatter counterparts. Most of the mass is still in the form of those tiny pipsqueaks, leptons. Not much changes from now until 3 minutes. Matter and antimatter are still going at it during this lepton epoch. After 3 minutes, let's just say, things get nuclear during the nucleosynthesis epoch. From 3 to 20 minutes, the universe cools to about 1 billion degrees, hitting the sweet spot for nuclear fusion, which occurs in spades. Basic atoms form, hydrogen, helium, and lithium, becoming the building blocks of the whole universe. This next epoch, the photon epoch, is the first epoch longer than a human can experience. It started 3 minutes in and lasted for 240,000 years. The universe is still hot plasma, but we are rapidly approaching the state we know today. Well, rapidly isn't entirely accurate. Each stage has been exponentially longer. It's the recombination epoch, and who turned on the lights? Even though photons have been present for millennia, it's only now that there is room for light to shine. The universe is now 3,000 degrees, and atomic nuclei have now individually captured electrons, making it possible for light to slip through. This period lasts for 60,000 years. The universe is now equivalent to a fog of mostly hydrogen, some helium, and a sprinkle of lithium. This is also the same period where we see that classic cosmic background radiation. The next 150 million years are pretty boring. The universe expands to the point where it is no longer dense enough to generate light on its own, making this epoch somewhat of a dark age. After the dark age, gravity begins to work its magic, forming quasars, or quasi-stars. These quasars emit enough radiation to reionize the now neutral matter in the universe. This phase is called the reionization phase and lasts for 1 billion years. Simultaneously, we got stars and galaxies forming and building the twinkling web of mass and energy that we've observed today across our sky. Our solar system formed 8 billion years in, and we humans show up about 14 billion years after the Big Bang. But due to redshift, we can see things billions of years back, part of the reason why we know this much about the universe. After that, the universe works pretty much the same as we see it now. But if the universe was formed in such a complex and brilliant matter, what of its demise? Will it be just as glorious a blaze, or will it be a cruel inversion, a slow and grueling extinguish of the flames of creation? Well, we don't exactly know on account of the universe not ending yet, but we do have some good guesses. The two main theories are the Big Chill and the Big Crunch. If the universe keeps expanding forever, eventually all the mass and energy will spread out far enough that nothing can interact or happen. That's the Big Chill. Kinda boring. But if the universe doesn't end up expanding forever, gravity will pull it back together, and crunch! It's all squished back together. But maybe all this energy and mass in one place will cause an explosion. A big explosion. A Big Bang! That is the Big Bounce theory, which loops back in on itself, like one of those YouTube shorts. So now you know, why does the universe exist? Scientists say it was the Big Bang, which sounds simple enough, but leaves a lot unanswered. What exactly does a Big Bang entail?